is saying every acid can lose a proton to become a base, and every base can accept a proton to become an acid. Species related in this way are called conjugate acid-base pair. What is an acid according to Arrhenius? So we need to know what an acid and a base is according to Arrhenius, Bronsted, Lowry, and Lewis. So according to Arrhenius, an acid is any compound that increases the concentration of hydrogen in solution. Okay, acid is a compound that increases the concentration. Okay, that increases the concentration of hydrogen, which we call protons, in solution. So an example that we can give is hydrochloric acid. When you look at hydrochloric acid, it's like this. In solution, it's going to break and then you are going to have hydrogen ions and then chloride ions. This hydrogen, because remember in solution you have got water, isn't it? Water breaks down to form hydroxide and hydrogen. So that hydrogen that is coming from the water plus this hydrogen coming from the acid makes the concentration to be even higher. So there is an increase. So that is the definition. But then what are the limitations? Because second part is state the limitations. The limitations of the of the Arrhenius definition of an acid. Now, one problem with this one is that not all acids are actually in solution, so it doesn't account for acids that are not in solution. So now the first limitation is that it only applies to water-based systems. So any acid that is not in water, that is not in solution, we don't consider it. So it does not explain the behavior, let's say, of a non-aqueous solvent. Okay, non-aqueous solvent. The second limitation of the Arrhenius definition is that it ignores hydronium. Hope we know what hydronium is. So hydronium is H3O plus. So it ignores these ions because sometimes what happens that water will react with another water molecule like H2O plus H2O, and then you produce H3O plus because one water will act as a proton donor. The one that has donated will now just remain with hydroxide. So compounds that increase hydronium, you don't account for them. We're only accounting for the hydrogen ions. Okay. And then it will also, another limitation is that it excludes acids without hydrogen ion. Examples of acids without hydrogen ion are those that are what we call Lewis acids. A Lewis acid is an electron pair acceptor. For example, boron trifluoride. This is an acid because it accepts a pair of electrons, but it is not accounted for. Okay. And then the fourth limitation is that this definition does not explain acid-base reactions that occur outside water. So those are the limitations. I hope that's okay. Please, if you have a question, feel free to ask. Okay. And then B is saying identify the acid-base conjugate pair in the following species. Now, acid-base conjugate pair an acid base conjugate pair differs. I don't want you to forget this one. Differs only by one proton, one hydrogen ion. Okay, so if you have got two compounds that differ by more than one, they are not conjugates. So the first example that we can pick, look at this. We have got acetic acid CH3COOH. So if you look at any molecule that has got one hydrogen less than this one, it means that it's the conjugate base, because the acid always has got more hydrogens. So the conjugate is this one. The next one that we can pick, look at which one can we pick? CH3. Okay, this one here, this guy, you can see CH3 NH3. It has got three hydrogens at the end, but this one here only has got two hydrogens. So this one is the base, CH3 NH2. So the base always has got fewer hydrogens. The other one that we can pick is so this one and this one. Okay, you can see those. They only differ by one proton. So those are also conjugates. So the acid in that case is the one with an hydrogen, HPO4. This one is supposed to have a charge of only a negative because it has got a proton. The one that has got no proton is the one now which will be PO4 with a charge of 2 minus. And then again, look at this guy. The chlorine that you can see, halogens basically preserve the charge, just like group 1 elements like sodium only preserve the charge. So this guy is actually NH4 plus. So this is the acid. So look at a molecule that has got one proton less than. You can see ammonia, it has got one proton less than. So NH4 plus, or you can put a Cl the way it has been given, is the acid for the base NH3. Okay, I think we've written everything here. Is there anyone that's behind? Anyone behind? I hope we are good. All right. The next question is saying, which of the following is or are not an acid-base conjugate pair? So we want which are not. So the ones which are not are those ones where they don't differ by one proton. For example, you can see HSC and H2SC, they are conjugates because they only differ by one hydrogen. This one has got one hydrogen, the other one has got two hydrogens, so they differ by one. So those are conjugates. But hydronium and hydroxide are not, because there is a difference of two hydrogens. Okay. And then for the other one, sodium fluoride and fluorine, these are not, because sodium fluoride is not an acid, it's a salt. And then fluoride minus is a base. So this can't be acid-base conjugate. All right. And then number 2 is saying calculate the pH of the following. A blood sample with a concentration of hydroxide of 1.20 times 10 to the power negative 7. So they've already given us the concentration of hydroxide. Okay. So what we can do is, since we know the concentration of hydroxide, we can calculate what we call pOH. So pOH is equal to negative log of OH, the concentration of OH. You need to know that the P of anything. So if I've got X, I put P in front, it just means negative log of that X. If I've got M, I put P in front, it just means negative log of this M. So pOH is just the negative log of the concentration of M. So if I'm UNZA, or the acidious boy, the P of the acidious boy will just be negative log of the acidious boy. Alright, so this is going to become negative log. Concentration of hydroxide is 1.20 times 10 to the power negative 7. So we just punch this negative log of 1.2 times 10 to the power negative 7. So this one has given me 6.92. But the question is asking us to calculate the pH. But you know that pH is actually 14 minus pOH. In other words, when you get a pH and a pOH, you add them, you should get 14. So this will be 14 minus 6.92, and that's 14 minus 6.92, so that is 7.079. Okay, so that is it for that one. The second one, we want to calculate the pH when the pOH is 4.3. Again, pH is simply 14 minus pOH. So this is going to be 14 minus 4.3. So 14 minus 4.3 is a 9.7. The next one, we've been told 100 mils of 0.01 mole hydrochloric acid diluted with 500 mils of water. So remember there is dilution here. You can actually calculate the initial pH and then find the final pH. But it's not necessary because we just want to find the pH after the dilution. Okay. So the first thing that we need to do is uh, let's find the number of moles before dilution. So number of moles before dilution is going to be equal to, okay, we can calculate that because the M, I just want to determine the final concentration. That's the M. So let me not even use this childish thing here for finding first the number of moles. Instead, let's find the total. So volume 1, V1 is 100 mils, all right? And then the first concentration C1 is 0.01 molar. What will be the second volume? The second volume is after you add the initial volume with the dilution volume. So that is going to be 100 plus 500, which is a 600 mils. But we don't know the second concentration, that is C2. We don't know this value. So when you use the dilution formula, C1 V1 is equal to C2 V2. So C1 here is 0.01. Now this is in molar. I'll multiply by V1. I'll not even convert to liters because I know even the mils will cancel out. The other side we're going to have C2 times V2, and V2 is 600 mils. So divide by 600 mils here, also there by 600 mils. So you see that the mils will basically cancel out. So we'll just remain with C2 being equal to 0.01 times 100. Let's see what that gives us. So it is a 1. And then 1 you divide by 600. So that has given me 0.00167, and this is in molar. So this is the concentration. Remember, this is the concentration of what? Hydrochloric acid. Now, one thing that you need to know is that the concentration of hydrochloric acid, because hydrochloric acid is a strong acid, so HCl, when it disassociates, the concentration of hydrogen is equal to the concentration of hydroxide. Okay, so the concentration of hydrogen chloride or hydrochloric acid is hydrogen chloride. If it's a gas, in aqueous we call it hydrochloric acid, is going to be equal to the concentration of hydrogen, and that is 0.00167 molar. Therefore, to find the pH, we simply take negative log of the concentration of hydrogen. Simple, isn't it? So this is going to give us negative log concentration of hydrogen 0.00167. So this is going to give us 2.78. Are we okay? Please feel free to ask again if you have got a question. D is saying 0.040 molar ammonia solution with Kb of 1.8. Now remember, we've been given ammonia. Ammonia is a base, NH3. So since it's a base, for you to use the Kb, you need to react it with an acid. In this case, what will be acting as the acid is going to be water. Now water is a liquid, and this is going to form, water is going to act as a proton donor because it's an acid, donating a proton to ammonia, so ammonia becomes ammonium. And then we have got hydroxide. So using now the ice table, we have got the initial concentration. The initial concentration of ammonia is 0.40. I'll not put anything for water because it's a liquid, so we don't include liquids when you're talking about Kb. But initially we don't have any product, so the initial concentration of the product is 0. And then they change. When the reaction starts happening, the reactant will start decreasing, so there will be a reduction of negative x. The products are going to be increasing by the same factor. Just make sure that the equation is balanced, because if it's a balanced equation, let's say if there was a 2 here, these 2 also come here. Okay, but it's balanced and there's no any constant. Is it even balanced? Yes, it is, isn't it? There's no constant. And then at equilibrium, you basically add the initial concentration with the change in concentration. So that will be 0.40 minus x. But please always know that if the value of the Kb that has been given is very small, the Kb given here is 7.4 times 10 to the power negative 6. Since it's very small, how do you know that it's small? Like from 10 to the power negative 3, negative 4, negative 5, negative 6, those are small values. You take this one because when Kb is small, it means that the value of x is actually going to be very small, so it's going to be negligible. So 0.4 minus x will just be the same as 0.4. And then here 0 plus x will just be x. And 0 plus x will just be x. So at this point now you can say, you can use now the equilibrium expression. We'll say Kb, the base dissociation constant, is equal to the concentration on the product on our balanced equation, that is ammonium, multiplied by the concentration of hydroxide divided by the concentration of ammonia. So the Kb is 1.85 times 10 to the power negative 6. That is because the concentration of ammonia, ammonium is x, concentration of hydroxide is also x. In the denominator, the concentration of ammonia at equilibrium is 0.4. So this is what we are going to work out. X times x is x squared, and this is going to be equal to, in the denominator we have got 0.4. This 0.4 is going to multiply with 1.85 times 10 to the power negative 6. Okay. Actually, it's supposed to be 1.8 times 10 to the power negative 5. I didn't write this well. Okay, so these are the ones that we are multiplying. 1.85 times 10 to the power negative 5 multiplied by 0.4 This is going to give us 7 7.4 times 10 to the power negative 6. So at this point now, what you do is you square root both sides so that you can remain with the value of x. Square root there and also square root here. Therefore, the value of x here, if you square root, is going to be equal to 2.72 times 10 to the power negative 3. So remember, the concentration of hydroxide at equilibrium was x. So this tells you that the concentration of hydroxide at equilibrium is actually 2.72 times 10 to the power negative 3. And it's the one that you use to calculate the pOH. So pOH is going to be negative log of the concentration of hydroxide, which is 2.72 times 10 to the power negative 3, and the pOH therefore is going to give us 2.57. Question is to calculate pH. So pH is going to be 14 minus pOH, which is 14 minus 2.57, and this is going to be 11.43. Does this make sense, guys? Is there anyone that has a question? Is this okay? Question 3. Question 3 is saying, answer the following questions on acid-base equilibrium. Calculate the hydronium concentration with pH of 2.0. So remember, pH is equal to negative log of the concentration of hydronium. Is just because the concentration of hydronium is the same as the concentration of hydrogen. Okay, so you can either use the concentration of hydronium or the concentration of hydrogen. It will give you the same answer. So pH is 2.0, and that is going to be negative log of the concentration of hydronium. Divide both sides by a negative, so you remain with a log the concentration of hydronium being equal to negative 2.0. For us to find the concentration of hydronium, remember a logarithm where the base is not showing is in base 10. So the base is 10, and this number that is this side will become the power, and it's going to be equal to the hydronium. That's how you convert a logarithm. If you have got log in base a of x is equal to 2, this is a to the power 2 is equal to x. So a to the power 2 is equal to x, or x is equal to a to the power 2. That's how you convert. So therefore, the concentration of hydronium in this case is going to be 10 to the power negative 2, which is a 0.01 molar. Okay, so B is saying calculate the hydroxide concentration with pOH of 0.12. Again, the pOH is equal to negative log of the concentration of hydroxide. The pOH is 12, and that is equal to negative log of hydroxide. Divide through by a negative, so log of hydroxide is going to be negative 12. So the concentration of hydroxide, therefore, the base of this logarithm is 10, the power become negative 12. So therefore, the concentration of hydroxide is going to be 10 to the power negative 12. So 10 raised to the power negative 12, and that has given me, oh sorry, okay, it will just be the same value. We can't simplify it further than this. Okay, 10 to the power negative 12, there's nothing that we can do really there. So we'll just put molar at the end. That's the concentration. Number 4 is saying the pH of a 0.06 molar weak monoprotic acid is a 3.44. What is the percentage of the acid that is ionized? So for you to be able to work out this question, you've been given the monoprotic acid HA. Monoprotic just means that it has got one hydrogen, as you can see. When it disassociates, you are going to have hydrogen ion plus A minus. So using the ice table, the initial concentration of the acid is 0.06. Initially, you don't have any product, so 0 and 0. The change in concentration, this is going to be negative x. This is going to be the product, remember the gain, so positive x and positive x. At equilibrium, the concentration is going to be 0.06 minus x. This one is going to be x. This one is going to be x. Now remember the way we find the value of x, actually the concentration, so we can say Ka. How do you find Ka? So for this one, there's no need for calculating Ka because that's the second part of the question. But the concentration of hydrogen at equilibrium, can you say the concentration of hydrogen at equilibrium is equal to x? And you know that pH is equal to negative log of the concentration of hydrogen. The pH has been given as 3.44. That is going to be equal to negative log concentration of hydrogen. Divide through by a negative and then come to find the concentration of hydrogen. So the concentration of hydrogen is going to be 10 to the power negative 3.44. You first divide by a negative and then you convert it to exponential. And this is going to be, let's see, 10 to the power negative 3.44 is 3.63 times 10 to the power negative 4 molar. Okay, so this is how much ionized. How much ionized? The question is saying how much ionized just means how much was converted to product. But the question is saying what is the percent ionization? So percent ionization, or the percentage of the acid that was ionized, you get the concentration of the hydrogen at equilibrium. You divide by the initial concentration of the acid. Actually, not really the initial concentration. What you get is the concentration at equilibrium. But you get the initial concentration because you're considering what has ionized, okay? And then you multiply by 100%. So this is initial, and this is at equilibrium. So the concentration of hydrogen at equilibrium is 3.63 times 10 to the power negative 4. The initial concentration of the acid 0.06, and then multiply by 100%. So this is going to give us a percentage ionization of 0.605%. I hope that's okay. Please, in case you are left at any point, feel free to be able to ask. Okay? Martin, your hand is up. Like for which one? So if it gives you a pH greater than 7, it just means that the solution is alkaline. If it gives you a pH that is less than 7, it means that the solution is basic in nature. Mm. Is that okay? Okay. So the second part is saying we find the Ka. Now remember, Ka is given as the concentration on the product. Remember, for this question, on the product we had H plus, we also had the A minus, and then on the reactant we had Ha. Okay. Now, what was the concentration of H plus? Remember, the concentration of H, it's there. The concentration of H and the concentration of A minus were both X. And we just calculated that X was a 3.63 times 10 to the power negative 4. So that's what we put here. 3.63 times 10 to the power negative 4. But because it's the same value, instead of me writing it twice, I'll just raise it to the power 2. And then we'll divide by the concentration of Ha at equilibrium. Now look at this. At equilibrium, can you see that the concentration of Ha is 0.06 minus X? So that's what you write. It is 0.06 minus X. X is what? It is 3.63 times 10 to the power negative 4. So if you get to punch it, so you first have 3.63 times 10 to the power negative 4 squared. That will give us 1.32 times 10 to the power negative 7. In the denominator, when you subtract these two values, you are going to get 0.0596. Then if you divide them, you are going to get 2.22 times 10 to the power negative 6. Okay. So please just feel free to ask in case I don't point at you, right? Because I'm not coming to check on the screen who has got a hand up. So just open your mic in case you have a question. Number 5 is saying calculate the pH of the following solutions. We have got 0.25 molar propanoic acid with a Ka value of 1.36 times 10 power negative 5. Okay. Someone has a question? Now, propanoic acid, you don't even need to know the structure. If you've done organic chemistry, I can tell you the structure, but I've not yet taught you organic chemistry. So just take that the propanoic acid is a monoprotic acid. It has only one proton. So just write it as Ha. So it is going to disassociate to form H plus and A minus. There's no need of writing the exact formula. So the initial concentration of the acid is 0.25. Initially you don't have any products, and then After the reaction starts happening, reactant will be decreasing by x while the product is going to be increasing by the same constant x. At equilibrium, you are going to have 0.25 minus x. But look at the Ka, it's very small, so we'll approximate this to just be equal to 0.25. And then this one will be 0 plus x, which is x, and this will be x. So therefore, the Ka is going to be equal to the concentration of hydrogen multiplied by the concentration of A minus divided by the concentration of Ha. Now Ka again is 1.34 times 10 to the power negative 5. Hydrogen concentration is 0.25 at equilibrium. Oh, sorry, it's x actually. So it is x, and then for A is also x, and then Ha is there 0.25. So this is going to be x squared is equal to 0.25 multiplied by 1.34 times 10 to the power negative 5. That is going to give us 3.35 times 10 to the power negative 6. So at this point, we square root both sides, and x is going to give us 1.83 times 10 to the power negative 3. So now that we know the concentration of hydrogen, which is 1.83 times 10 to the power negative 3, the pH therefore is going to be negative log of 1.83 times 10 to the power negative 3, and this is going to give us 2.74. So that is that. B is saying we've been given 0.1 molar aniline with a Kb value of 4.3 times 10 to the power negative 10. Now aniline is a base. Okay, it's a base. Don't worry if you don't know the structure. All you do is, if you don't, for an acid, if you don't know the structure, just put Ha. For a base, if you don't know the structure, just put B with hydroxide. So this one just now reacted. So this is in aqueous. For a base, you react it with water. Water will be acting as acid. Water is a liquid. And this is going to give you. So remember, for bases, water acts as what? As the acid, isn't it? A proton donor. So water will donate a proton to the B. So you are going to now have a B. And then you are going to have, let me put a hydrogen in front. Okay. I could have also put it this side, it becomes BOH2, but it doesn't matter. What happens when a compound gains an hydrogen is that it becomes positively charged. The water is going to remain as hydroxide, which is also in aqueous. So at this point now, you can write the ice table. The initial concentration of the base is 0.10. Water is a liquid, so we don't include it here. Initially, we don't have any products. A change is going to happen. The base is going to decrease by x, while the product will increase by x. At equilibrium, this is going to be 0.10 minus x, which is approximately just equal to 0.10, because you can see the Kb is very small. And then this one, x, is going to be 0, this one also 0. So the Kb base dissociation constant is equal to the concentration of the conjugate acid. You can see this guy that has been formed is a conjugate acid coming from the base BOH. So the concentration of the acid HBOH plus multiplied by the concentration of hydroxide divided by the concentration of BOH. So the Kb is 4.3 by 10 to the power negative 10. That is equal to the concentration of these two products is X. The other one is also X. The reactant is 0.1. So X by X, let me take it there. That is going to be X squared. 0.1 times 10, 4.3 times 10 to the power negative 10. That is going to give us 4.3 times 10 to the power negative 11. Square root both sides. X will now give you 6.56 times 10 to the power negative 6. Remember, this one came because of square rooting. So now to find the POH, because this value of X is actually the concentration of hydroxide. So it's going to be negative log of 6.56 times 10 to the power negative 6. And that is going to give us the POH is 5.18. So the pH therefore is 14 minus 5.18, and that is going to give us 8.82. I hope that is okay. For the next question, we have got 0.05 molar sodium benzoate with a Ka value of 6.3. So sodium benzoate, if you hear something that ends like that, we have got structures that we call esters. Okay, so for that compound, when you react with, it's actually coming from an acid. When you react with the sodium and then you form that ester. Now, basically it's an acid. The sodium is basically preserving the charge. Okay, so forget about the sodium in front. Okay, it's not really an acid. Okay, it's actually a base, because sodium is positive. Acids are also positive, so sodium can't react with an acid because they are both positive. Sodium will be attached to a base. It is the group 7 elements, the chlorides, the halogens that reacts with acids. For example, hydrogen chloride, hydrochloric acid, hydrobromic acid, hydroiodic acid. Hope you get that. That will help you to identify whether you're dealing with an acid or a base. So this is a base. If you don't know the benzoate structure, again just say, okay, this is sodium benzoate. Now sodium, remember, as I've said, it is just keeping the charge. Okay, so let's just say this is a base with a structure BOH. So it will react with an acid, which is water, and then you are going to end up forming same structure as the one we wrote earlier. I can even say BOH2, the positive charge there, and then hydroxide. So here, the ice table, the initial concentration of the base is 0.05. The product is 0. The change, this is going to be negative X. Products always increase. At equilibrium, 0.05 minus X, which is approximately just equal to 0.05. As you can see, the K is small. This is X, this is X. Therefore, the Ka, okay, for here now, someone has a question? Yes, please. Sorry. Mm-hmm. Okay. So remember, they've asked us to calculate the pH. But we are dealing with a base, and they've given us the Ka. We can't use the Ka. So the first thing that we are going to do is calculate the Kb. So Ka multiplied by Kb is equal to Kw. Okay. So therefore, that means that the Ka is 6.3 times 10 to the power negative 5. We don't know the Kb. Kw you just need to know it is 1 times 10 to the power negative 14. Therefore, the Kb is going to be 1.0 times 10 to the power negative 14 divided by 6.3 times 10 to the power negative 5, and that is going to give us 1.59 times 10 to the power negative 10. Now that we know the Kb, we can now say Kb is equal to the concentration on the product. We had BO H2 positive multiplied by hydroxide divided by BOH, and the Kb is 1.59 times 10 to the power negative 10, which is going to be equal to X, which is the concentration of the acid, the conjugate acid, and then times the concentration of the hydroxide divided by concentration of the base at equilibrium, that's 0.05. So X by X, that's X squared, and that is going to be equal to 1.59 times 10 to the power negative 10 multiplied by 0.05. That gives us 7.95 times 10 to the power negative 12. For us to remain with X, we square root both sides. X therefore is going to be 8.91 times 10 to the power negative 6. So we have found the value of X. Remember the value of X? X is basically the concentration of hydroxide, and that one we have found 8.91 times 10 to the power negative 6. Therefore, we are going to calculate the POH, which is equal to negative log of 8.91 times 10 to the power negative 6, and that is going to give us 5.05. A question is asking us to calculate the pH. Therefore, the pH is going to be negative log of not negative log, because we already know the pOH, so we use that formula. The pH is going to be 14 minus pOH, and that is going to be 14 minus 5.05, which gives us 8.95. Does that make sense, guys? The friend that asked, is that clear now? Okay, question 6. Consider a 788 mils of sodium lactate buffer with a pH of 6.38. We then add to it 138 mils of 0.37 mils hydrochloric acid. This addition gives the buffer solution a new pH of 6.27. What is the capacity of our sodium phosphate buffer? Okay, for our sodium phosphate buffer. Now, this is not supposed to be sodium phosphate. We have got sodium lactate and then hydrochloric acid. I think that was just something which was errored there. Now, when you want to calculate the capacity or the buffer capacity, number one, look at initially what have you been given? 180 mils of 0.37 molar hydrochloric acid. That is the hydrochloric acid that we have. So what are the number of moles of hydrochloric acid from this volume and the concentration? Okay, because remember we initially had a, a buffer, isn't it, with a pH of 6.38. Now what a buffer does is this: when you get an acid you add to a buffer, you are going to neutralize that acid. When you get a base you add to the buffer, you neutralize that base. So initially we have got a buffer, sodium lactate. So this one was just a mistake here. So initially our sodium lactate buffer is at a pH of 6.38. When we add the acid, okay, so this should even direct you what you are going to be finding. Because to a buffer, when you start adding the acid, the pH is going to drop because we are adding acid. Acid is low. Okay. So we are trying to add the acid. So we want to find how much moles of the acid did we add. That's why you can see that the pH drops from 6.38 to 6.27. So the number of moles of hydrochloric acid added is going to be equal to, how do you find number of moles? It's concentration times volume. So the concentration is 0.37 molar. Molar is mole per liter, or multiplied by the volume, which is 138 mils. Now the 138 mils can't cancel with the liters down, so convert it to liters. Remember we convert mils is on top, so put a mils down and then a liter on top. In 1 liter now I've got 1,000 mils. So the mil cancel with the mil, the liter cancel with liter. A simple way in which you convert is just say 138 divided by 1000. Every time you're converting mils to liters, just divide by 1000 or multiply by 10 to the power negative 3. It's the same. So this will give us the moles being 0.05106. These are the moles of hydrochloric acid that we added to our buffer. So now the next thing we need to determine, remember when we added these moles, the pH changed. So there is a change in pH. So we need to find the change in pH. The change in pH is equal to final pH minus initial pH. And in this case, we can actually do the opposite to say initial minus final so that the value can just become positive. But change we normally say final minus initial. But just know that we want the absolute value. So I'm putting it in these lines. So the final pH 6.27, the initial 6.38, and this is going to give us 0.11. It's going to be negative, but because we're in absolute bars, it's going to become positive. Okay, so the next thing that we need to find is now the buffer capacity. So how do you determine the buffer capacity then? After you find these two terms, buffer capacity, the symbol is beta. So buffer capacity is given as a change in the number of moles divided by the change in pH. So the change in the number of moles, it's the moles of acid or base that were added, and then you divide by the change in pH. So the moles of acid which were added is 0.05106 divided by the change in pH, which is 0.11. and this is going to give us 0.464. That is our buffer capacity. Number 7a is saying, I hope that's okay. 7a is saying calculate the pH of a 0.5 liter buffer solution. Yes, please. Okay. Calculate the pH of a 0.50 liter buffer solution composed of 0.7 mils molar of formic acid with that Ka and 0.5 molar sodium formate. So the first thing that you need to realize is this. This buffer, every buffer contains the acid and the base. So what happens is, so for the acid is HCOOH. If this guy disassociates the formic acid, you are going to formate ion HCOO minus and then hydrogen. Now what happens that you just don't want this negative to be there. That's why you end up attaching a sodium there. So that, remember I said that for bases, you always attach group 1 atom so that you just neutralize that charge. So this is the acid, and then this is the conjugate base. Okay. So we know the concentration of the acid, we know also the concentration of the conjugate. Actually, we know the concentration of the acid, yes, and the concentration of the conjugate base. And we know also the volume. So what we want to use here are basically the number of moles of what we have been given. Okay. Now number of moles, how do you find number of moles? Because we have got the same volume, number of moles like for formic acid will be number of moles is concentration times volume, isn't it? So get this value, you multiply with this value. That will give you the number of moles of formic acid. The number of moles of sodium formate will be this value multiplied again by the concentration. But because we're multiplying by the same value, 0.5 for both the acid and the base, we can just use the concentrations. We can use the concentrations. So for to calculate, I can decide. Now this is where you need to have some chemistry. I can decide to use the ice table, or I can use the Anderson-Hasselbalch equation. Now the ice table is going to just be a little bit wasteful of time. Why? Because I'll have to go and calculate the value of X. Once I determine the value of X, which gives me the concentration of hydrogen, that's when I come and find the pH. But let me just show you. You are going to finish yourself. I'm not going to use the ice table. So the concentration of the acid, you can see, is 0.7. The concentration of the base is not 0 in this case, it's actually 0.5. It's only the concentration of hydrogen that is a 0. The change, this is going to be the reactant, the change is going to be negative x, product positive x. And then at equilibrium, this is going to be 0.7 minus x, which will be approximately just equal to 0.7. This will be 0.5 plus x, approximately just equal to 0.5, and then this is going to be x. So the Ka is going to be equal to the concentration of HCOO minus multiplied by H plus divided by the concentration of HCOOH. So what I want you to do is, anyway, let's answer it together. We use both methods. So the Ka, you can see, is 1.77 times 10 to the power negative 4. Concentration of the H, you can see that the base is 0.5. Concentration of hydrogen is X. In the denominator, concentration of the acid is 0.7. To remain with X, X is going to be 1.77 times 10 to the power negative 4, or multiply by 0.7, and then we'll divide by 0.5. So therefore, this is going to give us 1.77 times 10 to the power negative 4 multiplied by 0.7 divided by 0.5. That has given 0.0002478. This is the concentration of the acid. Therefore, to calculate the pH, we'll take it here. The pH is going to be negative log of the concentration of the acid, isn't it? And that is going to be negative log of 0.0024778. So I'll just say negative log of this value, and that has given me 3.61. So what I've used here is the ice table. That is method 1. Now, if they've given you a buffer, the best method to use is the Henderson-Hasselbalch equation, and it depends whether you have got an acid and a conjugate base, or you have got a base and a salt. So there are two forms of the Henderson-Hasselbalch equation. So here we have got the acid and the conjugate base. So the way we calculate pH is pH from the Henderson-Hasselbalch. pH is equal to pKa plus log the concentration of the base over the concentration of the acid. Okay, so we come and determine the pKa. Now the way we find pKa is, remember I said P of anything is just negative log of that thing. So pKa is negative log of Ka. Okay, you can just put here pKa is equal to negative log of Ka, just in case someone doesn't know what will be happening. So we are going to say negative log. Remember the Ka is 1.77 times 10 to the power negative 4. And then plus log. The base, remember the concentration, the base, we said the concentration is what? It's here, 0.5. While the acid, the concentration is here, is 0.7. So if you punch negative log of 1.77 times 10 to the power negative 4, that is a 3.75, and then plus log of 0.5 over 0.7, that is a negative 0.146, add 3.75 plus negative 0.146, that gives us a 3.60. So you can see, so now you can decide which method you think is better, whether to use the ice table or to use the Henderson-Hasselbalch equation. The marks are all the same. B is saying calculate the pH after adding 50 ml of 1 molar sodium hydroxide solution. So this is basically the same question, with the one above. We have got a buffer, okay? We have got a buffer there of carbonic acid. But with that buffer, what we are doing is that we are adding sodium hydroxide. What do you think is going to be happening? So what will be happening is that the sodium hydroxide will consume some of the acid. So I can actually write an equation. So because this is a base that we are adding, it will react with the acid part of the buffer. The acid part of the buffer is the carbonic acid, isn't it? So we have got HCOOH. This guy will react with the sodium hydroxide. And what we are going to form, sodium hydroxide is a base. So a base is a what? Proton. An acid is a proton donor, a base is a proton acceptor. So one proton is going to move from this base and go to the acid. But forget about the sodium. The sodium is just preserving the charge. So if you remove one proton from the acid, it goes to the hydroxide, it becomes water. This sodium will just balance with the charge that will remain with the on the base. Okay? So you are going to have HCOO. Initially it's supposed to be COO minus. But because of the sodium, that sodium that has come from this guy to balance the charge. And then the other product is water, H2O. Because the hydrogen came from the acid and then it went on the hydroxide. We need to know the number of moles which are present initially for this guy, the acid. How do you determine the number of moles initially? The number of moles of the acid, you can see the volume was 0.5, the concentration was 0.7. So what will be the number of moles? So number of moles of HCOOH is concentration times volume. So concentration was 0.7. The volume was 0.5 liters. So this is going to give us 0.7 by 0.5. That's 0.35 moles. And then we also determine now what we are adding. We are adding the sodium hydroxide. So we can find the number of moles also for sodium hydroxide. It's also given by concentration times volume. Concentration is 0 point, is just a 1. And then the volume is 50 mils. So this 50 mils convert to liters, just multiply by 10 to the power negative 3 or divide by 1000. It's all the same. So it's basically 50 divided by 1000, and this is 0.05 moles. So what is this is telling you is that when you now want to use the ice table, the initial concentrations for the acid, not concentrations but moles, you use moles here, not concentrations, okay? Because the volume wasn't the same for the sodium hydroxide and for the acid. Initial concentration of the acid is 0. Not concentration but initial moles of the acid is 0.35. For the acid, for the base is 0.05. We don't have any products here. So when a change happens in such a way that the one that is small is going to be completely chewed. So between 0.35 and 0.05, which one is more? 0.05. So we are going to subtract 0.05 here. We'll subtract 0.05 here. And these are the same values that also add on the product. It becomes the change on the product. So therefore, if we subtract now, so at equilibrium, what we're going to see is 0.35 minus 0.05. And that is going to give us 0.35 minus 0.05. That is going to be 0.3 just. And then for this one, it's going to be 0. On the product, you can see the conjugate base is going to be just 0.05. Water is also 0.05. So therefore, after you do this, you can now use the Henderson-Hasselbalch equation to calculate the pH. And pH is equal to pKa plus log. The base in this case is this guy with a sodium, HCOO minus. The acid is the guy that has got an hydrogen. So pKa is negative log. The Ka, remember, is the same, 1.77 times 10. It was times 10 to the power what? To the power negative 4. And then plus log. The number of moles is what we use in this case. Number of moles is the same as concentration. If you just divide, of course, you can convert the number of moles to concentration. So the base is 0. Which one is the base? Okay, we have got 0.05, and then we have got 0.03. Okay, so these are the two, 0.05 over 0.3. So let's see what this gives us. Okay, there's something that I've not done on the concentration of the acid. Remember, this is the concentration of the acid that we have as at the moles of the acid. Here we found 0.3. By the moles of the base we have got 0.5. That's the ones that is going to remain. It is 0.5. But look at the top. It's not the only base that is present. Okay, we also have another base. Look, we have got 5 molar sodium formate. That is also a base. If you calculate the moles for this guy, please take note of that. The base that we are going to have at equilibrium is not just the sodium, or the base that is coming from the sodium. You also have the base on the buffer. So I didn't account for that, and that can be a problem. So let's account for that also. So we'll say the number of moles of formic sodium formate, which is HCOO minus. Remember the concentration was 0.5 from the equation. We'll multiply that by the volume, which is 0.5 liters also. And this is going to give you 0. If you multiply, it is 0.25 moles. This is telling you that therefore the number of moles of HCOO minus is equal to 0.25 plus this one from this equation, which is 0.05. If you add these guys, you are going to get 0.3. Therefore, if you come on this equation and say the concentration of HCOO minus, it is 0.3. The concentration of the acid, you can see at equilibrium, is also 0.3. And if you punch this now on the calculator, log of 0.3 over 0.3, that's a 1. Log of a 1 is a 0. And then you basically just have negative log of 1.77 times 10 to the power negative 10, or to the power negative 4. And that is going to give us 3.75. What has happened to the pH? Has it decreased or it has increased? So you should be able to relate why whatever that has happened like that. When you look at the initial pH that we had, initially the pH was what? Okay, this one was saying calculate the pH and we found the pH to be 3.6. Here the pH is 3.7. Why has the pH increased? Because we added the base. A base increases the pH. Does this make sense, guys? Is this okay? Okay. So number 8 is saying a 0.28 more of CH3NH2 with a Kb of 5 times 10 to the negative 4 is mixed with 0.09 more of hydrochloric acid and diluted to 1 liter. What will be the concentration of hydrogen? And they've given us the equation there. So what are we going to do for this one? Let's start with our equation. CH3NH2 is reacting with the hydrogen. The hydrogen is basically coming from the acid. And this is forming CH3NH3 plus. Okay. So what are the initial moles? The initial mole have got 0.28 of the base and 0.9 of the acid. These guys are mixed and diluted to 1.0 liters. In other words, you mix them and then you make sure that the volume is 1 liter. So since the volume is the same, we can still use the number of moles for calculation's sake. All right. So we'll start with the initial things. So the initial moles, we know them. And then when the reaction, so let's use the ice table again. Initially, the moles of the base is 0.28. The moles of the acid is 0.09. Initially, do we have any product? No. And then a change is going to happen. Remember, a change happens in such a way that you are trying to consume the smallest moles. So the smallest moles is 0.9. So subtract 0.009 both reactants, but products increase. So add 0.09. At equilibrium, so 0.28 minus 0.09, that will give us 0.19. This is going to give us 0. All the hydrogens have been chewed up, and this is going to be 0.09. Okay. So the solution therefore contains 0.19 moles of this base and then 0.09 moles of this product here. So this guy that you can see is actually the salt. Okay. This is a salt here. Or we can say it's a conjugate acid. So if you want to calculate the pH using, so here you have got this, you have got this is the base because you can see they've given us Kb. This is a base, that's why we are reacting with the acid. When you react a base with the acid, what you form is a salt. Of course, we can also say this is a conjugate acid of this base. So the Anderson-Russell-Bosch equation has got another version where we can use the concentration of the base and the salt. And in that case, what we calculate is not a pH, but a pOH. So pOH is given by pKb, not pKa, plus log, and you always start with the salt. The base comes in the denominator. For the other one, it was base over acid. So this is going to be negative log Kb is 5 times 10 to the power negative 4 plus log the salt concentration at equilibrium is 0.09. 0.09, and then the base is 0.19. So log of negative log of 5 times 10 to the power negative 4 is a 3.30. Log of 0.09 over 0.19 is negative 0.323. So this punched on our calculator gives us a pH of 2.98. Now that we know the pOH, the question is what it would be the concentration of hydrogen. We know the pOH, we can calculate what the pH. So pH is 14 minus pOH, which is 14 minus 2.98, and that gives us 14 minus 2.98 is 11.02. Since we know the pH, we can calculate the concentration of hydrogen. We know that pH is negative log of H. So 11.02 is negative log of H. So for you to find the concentration of hydrogen, divide first through by a negative. So the base here is in base 10. This will be raised to the power negative 11.02. Therefore, the concentration of hydrogen, and this is at equilibrium, 10 to the power negative 0. To the power 11.02 is going to be 9.55 times 10 to the power negative 12 molar. That is how you calculate the concentration. I hope that is okay. Okay, we have got one more question for calculating and then we are done, because the other one is just giving a definition. Determine the pH of a solution prepared by dissolving 0.47 mole ammonium chloride in 1 liter of 0.33 molar aqueous ammonia. A Kb of ammonia has been given there. So first thing first, we've been given the Kb. Okay, we can start with ammonia, which is the base, since we've been given the Kb for ammonia. Ammonia can react with an acid. Okay, I can just say H plus to give us ammonium. But let me say not H plus but water. Water acts as a proton donor, and we are going to have ammonium, and then we are going to have hydroxide. So again, using the ice table, okay, because the volume again is the same, we only have 1 liter solution here. So the volume is the same, we can simply use the number of moles. So the initial number of moles for ammonia is 0.33. On the product, we have got the moles of ammonium, sorry, that is 0.47 there. Initially, the concentration of this guy, the hydroxide, is a 0, okay, at the beginning. So ammonium chloride is the one that gives us ammonium ions, and that's 0.47. And we also know the Kb. So direct to, because we know ammonia is the base, ammonium is the salt. So we can go direct, determine the pH. We already know these quantities. So simply say, since we've been given a base, we found the pOH by saying pKb plus log the concentration of the salt divided by the concentration of the base. pKb is negative log of Kb, which is 1.77 times 10 to the power negative 5, and then plus log the salt concentration is 0.47 divided by 0.33, which is the base. So negative log of 1.77 times 10 to the power negative 5 is 4.75 plus log of 0.47 over 0.33, that is going to be 0.15. So 4.7 plus that guy 0.15, that gives us a 4.90, and so the pH therefore is 14 minus 4.90, and that is going to give us 9.10. Okay, so that is that. And then for the definitions, define a buffered solution. A buffered solution or a buffer solution is a solution that contains a weak acid and its conjugate base, or weak base with a conjugate acid. That's it. Okay. Solution of a weak, if it's strong, then it's not a buffer. So weak acid with its conjugate base, or it can be a solution of a weak base with its conjugate acid. So you need to know that when the acid is weak, it means that the conjugate guy is going to be strong. And if the base is weak, it means that a conjugate acid is going to be the opposite. So take note of that. So the conjugates are strong because what you start with is weak. Second part is a buffering capacity. So buffering capacity just refers to the amount of acid or base that a buffer can neutralize before the pH begins to change significantly. Because what happens is that, let's say if you have got a pH of 4, you have got a buffer solution. When you start adding an acid, the pH should remain 4. If you start adding a base, the pH should remain in that region. It will only change greatly if you add too much of the acid or too much of the base. That's what we call buffering capacity. Okay, amount of acid or base a buffer can neutralize before the pH begins to change significantly. Okay, so that is that one, significantly. And then a conjugate acid. What's a conjugate acid? A conjugate acid is a species that is formed when a base accepts a proton. Okay, species formed when a base accepts a proton, and the opposite, conjugate base. A conjugate base is a species formed when an acid donates a proton. When an acid donates a proton. So guys, this is your tutorial sheet, and that is how we go about it. In case you have got any questions, please feel free to get in touch with me. We can discuss these. 0974016268.